So I'm Ben Murray. I'm a research fellow at King's College London at Biomedical Engineering and Imaging Sciences. I work on deep learning for medical imaging across various different sort of sub-genres of that field. I've been a core dev team member of MONAI from the start of it, where my early focus was on helping to set the design philosophy of MONAI, design of a number of key features in MONAI, and I've been in various working groups throughout the lifetime MONAI working groups. At the moment, I focus more on large-scale refactors, particularly around pre-processing. So in 1.3, we had the laser resampling functionality that we introduced. And for 1.4, we started introducing geometry. So let me just break this talk up into three parts. The first part will be an introduction. And in the introduction, I'll basically be giving you all of the understanding that you need about the way geometry gets done in general in pre-processing pipelines. Then we can talk about 1.4 functionality, and for the third section of the talk, we'll talk about the feature functionality. So let's start off with image data versus geometric data. I'm going to probably interchangeably use the term image, volume, and raster. My apologies for that, but they all essentially mean the same thing for the purposes of this talk. So raster data is essentially a dense format of data where you have a sequence of values, each of which represents a particular point or region in a space. These points don't get their own specific position. It's kind of subordinate to the overall position of the image or volume. And so we don't need to basically provide a coordinate for each of these points. And this is the kind of data that MONAI and various other image processing libraries have provided lots of functionality for over the years. Now, if we compare that to geometric data, it's kind of the inverse of this. So geometric data is a sparse notation where only a certain subset of locations in space are noted, and each of those points has a position. So and then we have some way of interpreting those points to mean something. So if we go from on the right-hand side, if we go from top left to bottom right, so we have polylines here where the points are basically just connected in a sequence, and this can be a closed or open shape. We have here an example of a mesh. This is what we'd call a triangle fan mesh, where the points are essentially then indexed by a series of polygon indices to indicate which polygons they're part of. Then we have a region of interest where we really only need 2 points, one to specify the top left and one to specify the bottom right. And over here, we have the idea of a point cloud where you don't actually connect the points together. They are just a set of points that exist in space. So from a standpoint of what has been supported in terms of data in MONAI, we've always supported raster data in pre-processing. For 1.4, we're now introducing the idea that you could have geometry that is relative to raster data or image data. And in the future, we intend to support pure geometry data pipelines. So just looking briefly at the kind of formats you expect to see when you're dealing with raster data and geometry data, you're probably all familiar with raster data. When you're doing pre-processing, you'll typically have a number of channels. And then if you've got image data, you'll have height and width. And if you've got volumetric data, you'll have height, width, and depth. And they will define the shape of your tensor. So geometry data is slightly different. You can have a channel dimension at the start, and then you'll have a dimension P, which is the number of points in your data set. And then if your data is 2D, you'll have a third dimension of length 2, which represents your X and your Y coordinates. And if you're dealing with 3D, you'll have a dimension which is of length 3, which is your X, Y, and Z coordinates. So how do we manipulate geometry? So let's take a simple example here. In general, computer graphics makes use of this thing called a homogeneous transform matrix. And this can be a 3 by 3, but is typically more a 4 by 4 matrix that can represent a whole slew of different and useful transforms. So, for example, we can do things like zooming dimensions, we can do things like rotating, we can flip, we can move things around in space. And these have got some various useful properties. So, for example, you can define multiple of these operations, and you can chain them together by actually matrix multiplying them together and generating a composition of the matrices. So you can see here, we start off with a scale of 1.5 in Y by setting this value here in this matrix. Here we rotate our scene by 45 degrees. And this is how that's represented in a homogeneous coordinate system. And over here, we translate the scene by 5 pixels in X and 5 pixels, well, 5 units in X and 5 units in Y. And we can basically start off with an identity transform, and we can compose all of these together, and we end up with a transform that describes all of these operations in order, which is great. Another thing that we can do is, as long as our transforms are invertible, and nearly all of the transforms we are interested in processing pipelines tend to be invertible, we can invert each of these operations. So here is our inverted scale, here is our inverted rotate, and here is our inverted translate. And we can apply them in the opposite order and get back to where we started. So we transform points, and we can transform vectors as well by doing this matrix multiplication of our transform matrix and the point or the vector in question. And I won't go too much into detail of this. You can check the slides, and there's also a million resources out there that show you how to do this better than this slide does. But we can basically see that we can take a point that starts off at 2020, and if we scale by 1.5, rotate by 45 degrees, and then translate it by 5, that point that starts at 2020 ends up at minus 240. And if we're dealing with vectors, then we don't actually move the data around with the translation elements of the matrix here. So the point ends up at minus 735. And so if we imagine 2020 is up here, then minus 240 is somewhere over here. So it's in the appropriate expected location. So that's a whistle-stop tour of the way geometry transforms tend to be specified. So let's have a look at how we do hybrid image and geometry pipelines. So the first thing we've had to do is let me rephrase that. The first thing we needed to do is figure out how to do this, given that MONAI transforms are image-centric and not geometry or point-centric. What do I mean by this? What I mean is that all MONAI spatial transforms are designed to efficiently transform the data according to the characteristics of the transform. So we always want to use the best way of modifying the data according to the transform. So if we're doing flips or rotate 90s, to be honest, we're not going anywhere near geometry or geometric operations. We're really just performing operations on the tensor. These tend to be computationally very light, and they tend to not be lossy as well. So we're getting no floating point errors or sort of gradual degradation of accuracy. Sorry. If we, for example, are zooming the image, but we are not moving it away from the orthogonal, so we're not performing any kind of rotation on it, then we can use interpolation operations. But if we are doing things like rotation, then we might have to use a grid resample operation, which is quite heavy and lossy. And each of the MONAI transforms is implemented in terms of the best way to do that particular operation on image data. However, we have within MONAI, all transforms produce a homogeneous matrix of the sort that I showed you earlier. This was initially done for audit purposes, and then for the initial implementation of being able to invert the operations that are carried out on a pipeline, later repurposed for lazy resampling, and it's available through the affine property that we put on metatensors. So this is the way we've provided the ability to update geometry in 1.4. we've introduced this new method called apply transform to points, and there's a dictionary version as well. So essentially what it does is, if we have this pipeline that you can see here, where we apply a zoom augmentation, maybe, and we apply a rand augmentation, maybe, and we apply a rand crop, then each of these operations has updated the affine matrix of the tensor. And it's being performed on our raster data, so our image data and our label data, but we have a third field that we want to update, that is our geometry, that here I'm just calling ROIs for regions of interest. And what we can do is we can call apply transform to points on the ROIs, and we pass the image as the reference. And this operation can go and look up that affine matrix that describes the accumulated transforms and then apply them to our geometry, and our geometry is up to date. So one or two things that should be noted and that you must be aware of if you are using some of the transforms. So some transforms manipulate the raster data, but they don't change the volume of data geometrically. Instead, what they're doing is they're resampling the data and they're changing geometrically the resampling grid. So for example, resize. If we resize an image from one set of pixels to another, then we actually get this affine transform that is generated on the tensor, which represents the scale that we performed to the grid in order to create the description that the grid resampler uses to resample this data, or the interpolate backend uses to resample this data. Why does this matter, I hear you ask? So it matters whether your geometric data is defined in image space, which we would describe as being relative to pixels or voxels, or whether it's just defined in world space, which is physical units. Because what we don't want to do is we don't want to change the geometry when we, for example, call resize, because the coordinates in world space shouldn't change. However, the coordinates in image space would change because we've changed the number and the size of the pixels. So each of those pixels is now in a slightly different location in our data set. So as a result, if you wish to use transforms like resize, along with the pure spatial transforms, you should ensure that your geometric data is defined in terms of pixels or voxels. Now, there currently isn't MONAI support for this in this early release of the geometric resampling, but it's actually quite an easy thing to do. You can look up the pixel dims in your data, and you can use those to basically multiply your point coordinates. Although obviously we will support this with first class support in MONAI through various transform helpers. So another thing that you should be aware of is that, for example, if you are dealing with something like bounding boxes, which are a very common shape, they're often only defined by 2 points, a top left and a bottom right. So if you rotate these 2 points and still interpret them as a bounding box, you're going to get what you have here on the left, which is almost certainly not what you intended. Whereas what you really want, if you rotate a bounding box because you've rotated the data, is probably something more like this. So one of the features that we've provided is the ability to automatically convert your boxes to polylines, and you can convert them either into world coordinates or to image coordinates. So a few other things about what we've provided and what we haven't provided for 1.4. At the moment, loading point data is left to the user. I'll link some tutorials at the end of this where you can see how, for example, point data is generated and then brought into the pipeline. We're going to identify and prioritize the formats that we want to focus on supporting early on. And actually, that will largely come from you lovely folks who use MONAI and raise issues to say, can we please have this format supported? Similar to the way point data is interpreted, at the moment, we take tensors of points outside of dealing with bounding boxes, The points are considered the critical thing for us to transform. And if you then want to interpret those points in various different ways, i.e. as a polyline, as a mesh, and so on and so forth, that's currently left to the user. Again, we will identify and prioritize interpretations of points that people raise their hands and raise issues to get us to support. So that's 1.4 functionality. That gives us support of hybrid pipelines. Where we want to go in the longer term is to have geometry as a first-class tensor type that we can support as a pure geometry pipeline. So we don't actually need to have geometry specified relative to raster data such as images and volumes. So firstly, we're going to, by the way, I should caveat all of this. This design has gone through most of a release cycle of iteration. We feel fairly confident about the design. It doesn't mean that the design is not going to change. In fact, it probably will slightly change, but this thinking has all been destruct tested against various scenarios, and it's our current plan to implement at the moment. So we plan to introduce tensor kinds. We'll introduce a raster kind, which is for image and volume data, and it has the kind of metadata that you're used to, such as pixel dims, sort of like a world position for the volume. But we'll also introduce new metadata such as the effective center, and I'll give an example of why we will do that in a slide or two's time. And that because that is generally the image or volume center by default. We also have the geometry kind of data. So this will be all the different geometry data types. So it will be the kind of shape, which is, as I've mentioned, how to interpret the points. So that will include things like, for example, vertex indices. And we won't limit ourselves necessarily to just spatial point formats. For those of you who are familiar with geometry, you quite often have additional data that goes with points such as, for example, normals, which help with things like lighting objects. So we will almost certainly support point formats just beyond the position. So one of the things that we intend to do is we intend to adapt transforms for point data. In fact, we need to if we want to have geometry at first-class support. So let's take the example of rotating a 16 by 16 image 45 degrees. Now, if you were to do this in your typical geometry library, you're going to get this homogeneous transform matrix on the left here. However, when you look at a tensor that has been rotated by 45 degrees and it's a 16 by 16 image, you get this tensor, you get this homogeneous matrix on the right, which has these values here, which actually represent a translation. It's not a bug, it's intended, and it's because of the way that image-centric transformation works. So what you have to do when you want to rotate an image is you have to move that in order to have the expected user behavior, is you have to translate that image so that the center of the image is at the origin. You then rotate the image, and then you untranslate the image back to its original position. And so we can see here with this red circle, our 0.00 gets moved to 7.5 minus 3. So this is why MONAI tensors will output what I would call a non-canonical transform. Yes. So the thinking at the moment is that we're going to make our transforms pure geometry transforms and decouple essentially the definition of the operation from its application. And as I mentioned earlier, each transform currently does the most sensible operation for the type of transform. We would like to decouple that and create transform backends. So we can have a point transform backend and we can have a raster transform backend. And that raster transform backend will know how to take the pure transform, the canonical transform that's been defined, and then apply it to raster data. So for example, here, If the data has a grid, then we will do a grid resample of the data, including moving the image to its center, rotating it, and then moving it back to its original position. If it doesn't have a grid, we can examine that matrix and we can say, is the matrix orthogonal? If it isn't, then we can even do things like introducing a resample operation that doesn't require a grid. That's an extension that MONAI currently doesn't have. And in fact, PyTorch doesn't have, which is why MONAI doesn't have it, but we could still implement it. If the matrix does represent an orthogonal transform, we can check whether it's a unit scale and a unit translate. If it isn't, we perform an interpolate. And if it is, then we just perform a tensor operation. And this allows any spatial transform to transform image data the correct way without having to implement that for every single transform that performs spatial operations. It's reusable across all spatial transforms. And then it means that our implementation of all of our transform types is shareable across all transforms that we have now and all transforms that we might want to write in the future. It also means that it becomes quite easy to wrap libraries that produce their own geometric transform definitions. And then all we have to do, so if you remember your geometry classes in high school with the left-hand rule and the right-hand rule, and the fact that different libraries might have X, Y, Z or X, Z, Y as their coordinate systems, provided we can map the conventions of a given geometry library to the way MONAI expects those to be, then we can wrap, for example, ATK transforms in a MONAI transform wrapper and put it straight into a MONAI transform pipeline. And it also makes transforms a lot easier to understand. So that's everything for today. Please go check out the 1.4 geometry functionality. It will enable you to do a lot of things very readily using wherever you've got geometric data that is aligned with image data. Here are two of the tutorials that have been modified to use this new geometry functionality. And I'd also like to do my shout outs as well. Vikash has been the person who's really driven the requirements and the use cases for all of this work. Yun has been the person who's really driven all of the implementation of the 1.4 functionality in the tutorials. And I'd also like to thank Eric, Nick, Stephen, and other members of the core dev team for the lengthy discussions that we've had to really drill down into what we can do for this release and what we intend to do for next releases. So I'll finally finish. Lots of ways to contribute to MONAI. Please raise issues, please raise PRs. If you want to propose or join working groups, talk to Stephen Elwood, and here's a link for MONAI that I'm sure other people have seen. So thank you very much.